So now we're talking about the Rankine cycle, which is our model of the steam power plant. So it's very similar to the Brayton. Basically, you take your water, you pump it, which increases the pressure, then you heat it up, and then you send it through a turbine, and then the condenser rejects heat. And if we go ahead and look at the TS diagram, so normally we would have something like goes here, and it kind of looks like this parallelogram thing, right? But now, because we have different states, we have to superimpose like this dome thing, right? If you remember the states. So basically, the compressor, we're going to assume always that the input is a saturated liquid, because if we cool it down below that, then we just have to heat it up that much more, and it ends up not being as efficient. And if we bring it in with a vapor, we're going to get problems where it has like bubbles forming, and that can create shock waves. If you have air going into the boiler, it can start corroding. Not good. So you always want to send saturated liquid into the pump. Pump's going to increase the pressure, which is going to jump us up one of these lines. Then as we heat it up, it's going to follow along this constant pressure line, because we're assuming that it's constant pressure heat addition. Then we're going to get here. The condenser is going to, this is the turbine. So the turbine is going to decrease the pressure. It's going to extract work output. And then we're going to cool it down right here, back to state 1, and that's our cycle. So, let's try a couple of equations here. The work input into the pump is going to be the enthalpy at state 2 minus 1. This is our energy balance, basically, which is the same as, it would be approximately the same as specific volume times P2 minus P1. Remember that the water, because we're looking at basically saturated liquid and condensed, it's all liquid, which means we can assume that it's approximately incompressible, which means it almost has a constant specific volume. So V delta P, remember, if we're thinking about like W equals integral of P dV, but our V is constant, and then we have our change in P. So this simplifies to V delta P for incompressible fluid. The V that you would use, if you were to go ahead and actually calculate this, would be the V at state 1. So this is V1, which is the same thing as the saturated liquid, right? Specific volume at a pressure of either state 4 or state 1, because these states have the same pressure and these states also have the same pressure. The work output of the turbine is going to be equal to like H3 minus H4. We cannot do like the CP delta T stuff because we're not looking at ideal gases anymore. We'd also have Q in and Q out, so we'd have our Q in is H3 minus H2, and then our Q out is going to be H4 minus H1. And then we could also have the actual Rankine cycle, just like we saw before, but that's going to be like very, very similar to the Brayton. So basically the idea is that our compressor and our turbine might not be perfectly efficient. They're going to generate some entropy. And so we'd have an isentropic efficiency for both the pump and the turbine. So the isentropic efficiency of the pump and the turbine. So for the pump, we have a work input. So we're going to have the ideal over the actual, because the actual, in the best case, is equal to the ideal, but we're likely going to have to put in more work input, which is going to equal from our conservation of energy, the ideal change in enthalpy over the actual, just like that. We can't do anything with temperatures because, again, we don't have that constant specific heats like the air assumptions. And then the isentropic efficiency for the turbine would be our actual work output over our ideal, and this would equal H3 minus H4 actual over H3 minus H4 ideal. And again, you could flip each of these as long as you're consistent between the numerator and the denominator. It's not going to change anything. Now for the reheat, this is a modification where basically after the pump, we boil it, we heat it up, we send it through one turbine, and we reheat it, we heat it up again and send it through another turbine. So looking at our diagram, pump it, then we're going to heat it up, then we're going to extract work to a turbine down to state 4, then we're going to heat it up again back to the same temperature as what we have up here, then we're going to use our turbine to extract work, And then we're going to come back here, and you can see this increases the area of the shape, which is going to give us more network output, ideally. So the network output, WNet, in this case, is going to be the combination of the work from the turbines minus the pump. So we'd have WT1 plus WT2 minus WP. If you're looking at intercooling, so if there were two pumps and in between it you had like a heat rejection, then you just do a minus WP1 minus WP2. So yeah, and then most of this is going to be the same, right? Our efficiency is still WNet over Qin. Our Qin is now going to be basically the heat input from both the boiler and the reheater. So we'd have like an H3 minus H4 plus, sorry, this should be an H2 because we're looking at the boiler. And then we should have like H5 minus H4. So this right here is the Q of our reheat, and then this right here is the heat of the boiler. Our Q out is just going to be across the condenser, so we're just going to have our Q out is H6 minus H1, and then the work from the turbines, you would just look at H4 minus H3, or H6 minus H5, and then the pump would be 2 minus 1, right? So it's very similar to what we were doing before. Again, we're just looking at like applications, like certain ways that you could set this up. Now, one of the modifications we could have is the regenerator, but because we're dealing with different states, it can't work the same as just taking the exhaust from our turbine and basically pumping it in before the boiler right here, because we have to ensure that like things going into the pump are saturated liquid, and then it comes up here and the turbine is at a gas, and then we bring it back down to a mixture. Right, so basically our modification here is going to be we're going through the turbine, right? And then what actually happens here is we have something called bleeding. So normally the turbine would just take all of this and it would go to the condenser, right? But what we do is we bleed out a certain amount of the turbine, like fluid, at a higher pressure, not necessarily this pressure, kind of like intermediate. So state 6 would be between 5 and 7 in terms of pressure. So then we take this down, we reject all the heat. So if we're looking at this diagram right here, right? So I take it down to 7, reject all the heat. Then I pump it up to the pressure that this guy's at right here. And then I mix together 6 and 2 into a mixing chamber. And now I have state 3, which is right here. So 6 is going to cool down, 3 is going to heat up until I'm at this saturated liquid. And then I'm going to pump it up to the final pressure I need, heat addition from the boiler, and then I'm going to do the same thing. So in order to figure out how much it's going to bleed, we have a quantity called Y, which I think is usually just called the bleed. So Y is equal to the ratio of the mass flow rates from here to here, basically. So our Y is equal to m dot 6 over m dot 5. And this is where we got to be careful, because normally for all this stuff we've had so far, we've just had an m dot. And that's because it's basically flowing through one big circuit, right? So our fluid would go here, up to here, around here, like it all just has one line it can go through. Now, we're splitting the lines at the turbines. We're splitting it so some goes here and some goes here. And then we're recombining them at the mixing chamber, which means that the mass flow rate is going to be the same across all of these pipes. But then we're going to have a different mass flow rate through here, and then one more different mass flow rate through this channel right here. So you can kind of think about it as like a circuit of like different currents in different sections. Anyway, our heat input is going to be just from the boiler, right? So this is going to be an H5 minus H4. The work output from the turbine is where things get a little bit more complicated. One thing you could do is you could just go through the full like Q minus W has to equal like m dot 5, H5. This would be the input, so technically we would want to subtract this, right? And then we'd have like our m dot 6 H6 plus m dot 7 H7. And then you would use the bleed and the fact that you have conservation of mass. So you could also say that m dot 5, basically the input of mass flow rate has to balance with the outflow of m dot 6 plus our m dot 7. Anyway, you could work backwards from that, or you can just kind of like think about intuitively what's going to happen. I think is a little bit easier to understand, and it's also a little bit faster because you don't have to work through this every time. So basically, all of the mass in the turbine is at least going to go from state 5 to state 6, right? Which means that we can say that we have H5 minus H6 per amount of mass flowing through the boiler. I guess I should be more specific here. We're talking about the work output from the turbine per unit mass flowing through the boiler. Okay? Now we also need to consider the fraction that goes from 6 to 7. So if we have basically y percent going through here, then this side is going to have a 1 minus y percent coming through it. Right? So if we're bleeding like 10% here, then 90% will be 1 minus 10%, right? And that will be coming out here. So then we need to add 1 minus y for every unit of mass flowing through 5 times H6 minus H7, because the 1 minus y fraction that's going through all the way goes from 5 to 6, all of it goes from 5 to 6, and then that 1 minus y fraction goes from 6 to 7. So if we add these, we're getting the total work output from the turbine. And then the pump, usually all of our specifics in this case are going to be in terms of m dot across this main channel right here, where it's all combined, just because it makes it easy. If we're all talking about the same per unit mass flow, then we can add them together without having to worry about if they're compatible. So the work for the pump per unit mass running through the boiler is going to be 1 minus y, because this is the percent that goes through the pump per unit mass coming through the boiler, right? Times WP1, and then you could have a WP2 right here, right? We also have to consider WP2, but this right here, because we're on the main line, this is just going to be our full m dot, so we don't need to add a 1 minus y here. And just to be clear, our WP1 would be like our H2 minus H1, and then WP2 would be our H4 minus H. Now on top of that, we can also have what's called a closed feed water heater. So the idea with this one is that instead of a mixing chamber, we instead basically just have like our heat exchanger right here, which means that state 7 coming through here can be at a different pressure from this state right here. So we go ahead and we look kind of just what's happening. First, we pump up our water to a high pressure. Then we send it through here where it's going to gain some heat but not change pressure. Then our bleed from our turbine, our bleed from our turbine is going to come through here. It's going to loosen temperature, right? And then we're going to pump it up to basically the pressure of the boiler. So you can see that this entire line right here has to be the pressure of the boiler, because our mixing chamber mixes things that are at the same pressure. So everything along this entire line right here, up to here, and up to here has to be at the same pressure. Same thing with this right here and this right here. So if we go ahead and we look at the diagram, and then I guess just to be complete, right, boiler comes here to turbine, and then we condense, we reject, we add heat here, we reject heat here. So what's happening is state 1, we pump it up to state 2, right? Then we add some heat, it's going to get to state 9, and then we go through the mixing chamber, it's going to go up to state 5. Q in brings it from 5 to 6, and then the turbine is going to go back down to 8 if it goes through here, or it's going to go back down to 7 if we're bleeding it, and then it's going to get cooled down to state 3, at which case we're going to pump it up to state 4 here, and then it's going to get cooled down to state 5 as it gives some heat to the feed line. This right here is called the bleed line, and then the one that goes down to the condenser is called the feed, or the feed water. So, looking at this one's going to be a little bit more complicated. In terms of like actually solving problems, you're probably going to have to end up using conservation of energy and mass on some of these systems. So like this mixing chamber right here, right? I could be like, okay, well, I know that the influx and the outflux have to balance, right? So I know that per unit mass coming through the boiler, my output is going to be like H3 m dot 3, which is the same as m dot 5. And then I'll have a y. Come on. And then this will have to balance with, y m dot. Actually, the y here is not where we want to introduce it, because if we're just thinking in terms of conservation of energy, we just have m dots and h's, right? So this would be m dot 6, h6 plus m dot 2 H2. And then what we would do is that we would use the fact that Y is the ratio of m.6 to m.5, and we would plug that in here, and we can start solving for our different like m dot values or our Y. So that's definitely going to be useful. You're probably going to have to do some conservation of energy and mass on your feed water heater, just because that's like the critical component where things are getting split, or the mixing chamber. So going back down to the closed right here, just real quick, we're still going to have the same Y. Y equals m dot, I guess the numbers are slightly different now, so I'll have m dot 7 over m dot 6 now, right? Because it's the ratio of what's bleeding out to what we have right here. And then if we think about some conservation of energy in terms of this pump, we would have like a m dot 7 h7 plus, and then our other input is this m dot 8 h2, because m dot 8 is the same as m dot 8 is the same as m dot 2. All of this has to balance with our m dot 7h3 plus m dot 8, because these are the same mass flow rates because they're connected lines, right? M dot 8 times our h9. And then the other conservation of energy we could do is for the mixing chamber. So in this case, we would have an input of our m dot 8 h9 plus our m dot 7 connecting on this line times h4 has to equal our output, which is m dot 6 h5, because all of this is the same m dot, right, flowing through this entire thing. We still have our y, and then in terms of like conservation of energy, m dot 6 equals m dot 7 plus m dot 8. There's a lot of equations I could throw at you, but at this point it's nothing new. Like, we're just basically analyzing conservation of energy in a different context. The only thing that's really new about this is the bleed, and it really depends on what kind of problem you're solving. But there's a lot of stuff you can do. You can analyze the energy here or here or here, depending on what you're given and what you're asked to do. I think as long as you really understand like what's going on with what equations can we use and what's happening with this and the diagram, I don't think I would worry too much about like what's all of the equations I could use. I think it's more important to like understand where this equation is coming from, right? Because then you're not limited by like what you can memorize. So yeah, that's it. This is actually like the last thing we're going to talk about. So that is wraps for thermo. I hope you learned something new, and I will see you later.